All right, we're going to talk about nuclear reactions today. We're going to spend the whole day on nuclear, and we're going to only spend one day on nuclear. That's it. So we're going to be going through all of this about nuclear chemistry, and I think you will have a better understanding and maybe less of a fear, if you had a fear, of nuclear when we finish with this. So nuclear chemistry, we're going to start off just describing it in general, and as you know, it only involves the nucleus. We are not talking about electrons with nuclear chemistry. Now, starting next week, we are going to deal with electrons, and pretty much the rest of the semester it's going to be electron chemistry, but right now it's nuclear chemistry. So a radioactive isotope is unstable and spontaneously emits energy to form a more stable isotope that isn't radioactive. The key to radioactive isotopes that I want everyone to understand is that it's radioactive to start with, and it's giving off energy, but it's changing to something that's not radioactive. That's, I think, where we all get confused. We think that it's radioactive forever. It's not. It changes, and we're going to look at some specific examples of when it changes and what it changes to. But I want you to get it in your head that it does not stay radioactive and being unstable forever. It changes into something that is not radioactive. What is radioactivity? It is the nuclear radiation emitted by a radioactive isotope. It's the nuclear radiation emitted by a radioactive isotope. The types of radiation are listed here in the table. As far as what I want you to know out of this table, obviously I want you to know the names, alpha, beta, positron, and gamma. And I also want you to know the symbol. As far as knowing the exact charge and the mass, no, I don't care that you know the exact charge and the mass. What do you see out of this table, though, maybe that's interesting about what I'm not asking you to memorize? Anybody see anything in there that's interesting? What do you see that's maybe different about one of them or two of them? What do you see? Alpha particles are the only one with mass. That's exactly right. The alpha particles have mass. Nobody else does. And so they are the only ones that have mass. And that is what I wanted you to see, the fact that they do have the mass. So let's talk about the alpha particle first. It is a high energy particle. High energy particle that contains 2 protons and 2 neutrons. It has a charge of +2, and it has mass. It is not used in medicine very much at all. Why do you think? Why do you think it's not used in medicine much? It tells you. What does it have? It's too heavy. It's not used in medicine because it's too heavy. It moves too slowly, and it doesn't penetrate well enough to be useful in medicine. You can be protected from alpha particles with just lab coat and gloves, and it is not used much. So I do want you to know it is an alpha particle. I want you to know that it is a type of radiation, but it is not something that's going to be used in medicine. As far as having you memorize the words high energy particle that contains 2 protons and 2 neutrons and it has a charge of +2 and has mass, no, I don't expect you to memorize all that. Yes, I want you to know it has mass. Yes, I want you to know it's not used much in medicine. So then you say, well, why did you even write this? I wrote it as a review for last day. Tell me about anything you know about protons. They have a positive charge and they have mass. What would be the charge with 2 protons? +2. What do you know about neutrons? No charge, but yes, mass. So if this has mass and this has mass, the total mass is 4 AMU, yes? And would that make sense of why it has a +2 charge? So that's pretty much just a review. As far as memorizing that about alpha particles, no. But I want you to know it in the sense that you know it from other classes. As far as if I ever said to you, something has 2 protons, you're going to say +2. If here it's got 2 protons, 2 neutrons, you're saying 4 AMU. That's what I'm wanting you to start remembering, and that's why I even wrote it. So beta particles are used often in medicine. They are high energy electrons. High energy electrons, no mass. High energy electrons, and they basically have no mass. They are often used in medicine. And that's why it says beta is used widely in medicine, often used in medicine. You do need to wear a heavier lab coat, heavier gloves, even if you do, it may still cause burns. It can cause damage to the skin. But it is used widely in medicine, and we will see where it is used and where it is emitted by iodine-131 in a little bit. But it is used a lot in medicine. The positron is the opposite of beta. It has no mass with a positive charge. It has no mass, but it does have a positive charge. And if you are like me, you want to know how. And I can't tell you how. So I apologize. I don't know why. It doesn't make sense that it would have a positive charge and no mass, because what gives a positive charge is a proton, and it doesn't have a proton, and proton has mass, so I'm sorry, I don't know the answer. But it does not have mass, and it does have a positive charge. What I want you to know is something that you've heard about before. Positrons are used in PET scans. And what does PET scan stand for? PET stands for positron emission tomography. Positron emission tomography. We'll talk a little more about PET scans in a little bit. Gamma rays are high energy radiation. They have no mass, no charge. They are energy. They are not matter. They're actually on the same spectrum as X-rays and ultraviolet rays. I think the confusing thing for us is we sometimes don't realize there's something besides matter. But it's pretty easy to think about that. Think about a campfire. By the way, it's going to get cold next week. So have your campfire next week, not this week. Did you know this already? Oh, because you're hot now? Yeah. No, it's supposed to be like 49 by next Saturday. That's a little chilly. Whoa, did you? Goodness. Yeah, I'm telling you. That's cold. So go home this weekend and get your winter clothes, maybe, okay? Okay, wow. I don't know. All I know is what the weather forecast says for next week. Okay? Okay. Anyway. So you've got the campfire next weekend to stay warm. Not on campus. So you've got your campfire, and what is the campfire putting off? Heat. What else is it putting off? Light. Can you take that light or that heat and put it in a ball and take it home with you? Why not? What is light? Energy. What is heat? Energy. It's not matter. And I think that's one of those deep thoughts that you haven't thought about maybe, but it's not. You can't take it. You can't put it in your hand. And that's what gamma rays are. Gamma rays are energy. They're not matter, they're energy. Okay, very high energy, much higher than heat off a campfire, much higher than light off of the campfire. They're very high energy. And they travel extremely quickly, and yes, they are used in medicine, and they do readily penetrate body tissue. You basically can't protect yourself very much from the gamma rays, but they are still useful. Now, let's talk about how they could be useful, okay? When someone is going to undergo gamma radiation, chances are the purpose of it is the risks are not great enough to cause you not to do it. The benefit is greater. But at the same time, let's say that I have a tumor here, and let's say that they are focusing gamma rays on this tumor. Is that going to kill the skin right here? Yes. It's going to kill the skin right here, definitely. Why? Because it's very, very high energy. What's the purpose of it, though? What's the purpose of zapping me with gamma radiation or zapping the tumor with gamma radiation? To kill the cancer cells, to kill the tumor cells. That's what the purpose is. And so your options, if you have a tumor, let's say I have a golf ball tumor right here. The options are what, basically? Surgery, or shrink it, or maybe chemotherapy. And hopefully one of those options will hopefully kill it, get rid of it, move it on. But typically, would you want to do surgery on a tumor that is connected to other things? No, and you all know this. So instead, what do they lots of times do? They'll either do chemotherapy or radiation, in the process doing what? Shrinking it. And yes, does it kill the area around it? Yes, it's going to kill the area around it. But that's a minor problem compared to going in. If you were to go in and cut it out, what's the problem there, potentially? Leaving part of it behind, and or leaving some of just the cancer cells behind. And evidently, from what I've read, when you have cancer cells, they grow so quickly anyway, and if you cut on them, that like excites them even more and causes them to go just bonkers. And so the goal is to shrink it enough, kill all the cancer cells around it, then go in and take it out, and hopefully you get everything out. And so yes, is it going to damage? Yes. Am I being irradiated? Yes. But the benefit outweighs the risk. And that's what medicine has to decide all the time. All the time. Any drug you take, anything you do, does the benefit outweigh the risk? And that's just what you have to, that's the purpose of finding out new information, basically. Now, It's used in medicine, and it's also used in the food industry. Now, I'm curious, did any of you before just now know that it was used in the food industry? Lots of times I'll have somebody who's heard of that before. Any of you had a nutrition class? They talked about that? A couple of you? So our food, much of our produce is actually irradiated. Now, when I first heard that, I was like, what? I don't like that. I mean, that was my immediate reaction. I was like, I don't want my food irradiated because I didn't understand it. And then the more I learned about it, I decided, okay, maybe that's not a bad thing. So let me ask this question, first of all. Just saying that, is anybody like, ooh? Did anybody think that? A couple of you are like, that doesn't sound good. Okay. Some of you just don't care. That's okay. So the fact that it is irradiated, what purpose does that have? That's where you've got to get you'll get rid of the yuck once you know the purpose. So let's go backwards. Let's go to Florida, and let's go to the field, and let's pick strawberries. So we're going to go pick strawberries, and when we get the strawberries picked, I don't know exactly what they put them in the field, but they get the strawberries picked, then they bring them in, and chances are, I've never been to a strawberry packing plant, but this is my assumption based on what I've seen other things get packed. So they bring in the strawberries. They're probably going to dump them in a water vat. It's all mechanical. They're washing in there. They go out on a conveyor belt. They're draining. And then they're going to go all the way on the conveyor belt. You're going to have your packing people, and they're going to be packing them, picking them, throwing out the bad ones, putting them in the cartons. Do you know the trays they come in Walmart or in wherever you go to the store, the big cardboard trays? You know what I'm talking about? Okay, so they pack them in there. Then that goes down, and it gets put into the pallet, and then they shrink wrap it, and you got a pallet of strawberries. Everybody with me? Okay. Then that pallet of strawberries goes through the radiation chamber, and they're zapped with gamma rays. And then they go on, get in the truck, and sent to Bowling Green. Now, what is that doing? What is that gamma radiation doing? Killing the bacteria and the fungus. That's what it's doing. Now, you still say, well, I don't like that. That's not good. But the strawberry, it still has living cells in it, yes. But when you picked it, did you separate it from its growth? Yes. So it's not growing per se anymore. So it's dead, sort of, when you picked it. What are you killing with the gamma radiation? You already heard him say it. What are you killing? The bacteria and the fungus. Will it last longer in your kitchen? Yes. That's why they do it. That's why it's done that way. I have gotten strawberries before that still have sand on them. Have you ever gotten strawberries that had sand on them? In fact, yesterday I washed celery, and it was black dirt on the celery. I mean, it was gross celery. I mean, it was like dirty, dirt celery. But what was interesting is it was not deteriorated. It wasn't decaying. It was just plain dirty with dirt, soil. Now, common sense, I hope, should say if it has dirt on it, it had bacteria on it. But it wasn't decaying. Why not? Because it probably had been irradiated, because that was not, it was like at least a week or two old in my refrigerator. And it was not decaying. So it might have had dirt, but it had no fungus or bacteria on it because that had been killed. So is the food that has been irradiated safe to eat? And the answer is yes. Yes. Now, you still say, well, I don't like that still, though. Okay, let's think of another approach, not exactly the same thing, but sort of similar. Today I mowed the yard. I was outside and I was just mowing the yard, and I got all kinds of sun. I came in here to you. Are you scared to be around me? But I have been irradiated with ultraviolet radiation. Is that going to hurt you? Now, you're not eating me. I agree. You're not eating me. But it doesn't hurt you. Who's it hurt? Me. It's hurt my skin, but it doesn't hurt you. All right? So you still say, well, that's not exactly the same. Okay, let's go another one. Well, first of all, you've all eaten irradiated food and you're alive. I guess that's a good thing. But let's go another one. Dental hygiene. UV cleaners for the toothbrushes. Some of you that aren't dental hygiene, you know what I'm talking about. The little Sonicare chamber has a little ultraviolet, and you can buy an ultraviolet cleaner for your toothbrush too. Ultraviolet radiation kills some bacteria. You put your toothbrush in there, and then you put it right back in your mouth. So in essence, you are putting in your mouth irradiated bacteria. Does it hurt you? Evidently not. So it doesn't hurt you. Interesting thing is that food that is labeled as organic by the USDA cannot be irradiated. The people that make the decisions of what can be called organic say that if it's irradiated, it cannot be called organic. Now, personally, I think that's ridiculous because irradiation has nothing to do with whether it's raised with organic methods or not. But somewhere down the road, somebody said we're not going to let it be organic and irradiated. It can't be. Now, if any of you buy organic produce, and you can tell me the answer. I feel like I already know the answer, but if you buy organic produce and you've bought the same thing that was not organic, which one went bad faster? The organic. Now, does that tell you why? It's not irradiated. My mom, over the weekend, I was there, and somebody had bought her some carrots that were organic. And I don't know that they even meant to, but we were like getting them out, and they were nasty. I mean, they were like slimy. And she said, man, those have been like wet the whole time. You know, sometimes you get the bad carrots, they've just got water in them. These things were like slimy. They were yuck. They were not good anymore. And she hadn't had them very long. And it didn't dawn on me until after I got back home and was talking Monday morning, or yesterday, I guess it was, that I realized that's why. They were organic, and they had not been irradiated, so they're not going to last. And that's one of the reasons. The sources of gamma, cobalt-60 emits gamma radiation, cesium-137. I don't know which one they use, but it's an isotope that emits. They get that element, isotope, and then use it in their machine, for lack of a better. I don't know. I don't have any idea how much it takes. I do know that the girl that taught me more about this, because I was like, immediately when I heard this, I was like, what? I mean, I was like mad about me. You cannot tell me my food's, I was like, come on, that's crazy. And anyway, she was a Goldwater scholar, and the summer before I started teaching this class, she was a graduate student in chemistry, and she had been in California at a nuclear short course, and she'd be the person I needed to ask, and she's not here any longer, but she was the one who told me all about this, and she was in California, and they irradiated food. They did the process, and they went to a place that did this, and she told me a lot about it, but I don't know that answer. The picture I have seen, it was a simplified picture, because it's just a machine, and it's like it goes through this, and it's a lead chamber, really, really thick lead chamber, and it just goes in and zaps, and it's just like an X-ray. You know how when you have an X-ray, they just hit that button, you hear that noise, and it.
I wonder if like the people who work there,
I'm sure they are badges, which we're going to talk about, and they check them. I'm sure it's very, very. They may even wear lead aprons in addition to having. I don't know. I'm sure it's. You would definitely hope. Yeah, you would definitely hope that they're protected. But, let's say that somebody still says, I don't like this. What's your alternative? What is it? Well, buy organic or what? Grow it yourself. Why do you think they do this now? How many of you have a garden? So maybe 10, 20% maybe. How many of you raise your own meat? Okay, a couple of you. Do you see why they do it? We're spoiled, rotten brats. We don't take the time to raise our own food. And you don't have the means. You don't have the availability. You don't have the time. You don't have the space. You don't have the, that's why. But they used to not do this when everybody had a garden and had their chickens and their cow, and they didn't do that. So and because we now ship food from California to Kentucky, we want our grapes. They're 88 cents now at Kroger this week. And strawberries are $1.25 at Meijer, so just so you know.
Is it just produce?
No, it's actually meat too. They do meat too. I don't think all meat is done, but some meat is done. Some meat is done, yeah. So it's kind of interesting. So one of the reasons I tell you guys this is because, one, it's something that I learned that I thought was interesting and I didn't know, and I figured if I didn't know it, you probably don't know it. But the other thing is, you all are the decision makers for me in a few years. You're going to be the people in positions making decisions. And unfortunately, many people in decision-making positions don't know anything. There are people, for instance, who are running for office in Kentucky, and they have really fussed about rental property and renters' rights, etc. They don't even own rental property. And they fuss about stuff like that. And so it's really bothersome for people who do know a little bit when other people make decisions that don't know anything. But I think it's a shame that the people that are in those positions of power don't take the time to learn. And that's what I try to teach you guys, different things to make you interested and realize, go find out if you don't know it. And the sad thing is we all don't know what we don't know. That's kind of a dumb statement sounding, but we don't even know we don't know it until you expose yourself and read and talk to people that might not be in your normal circle. Then you learn what you don't know. And I think that's better. The other thing is as you know, I'm a big agriculture advocate, and one of the things that goes right along with that irradiation of food is mass production of like chickens or beef or pigs or whatever, and people fuss about like chicken houses. They'll fuss about stuff like that. Well, if you have never raised chickens on pasture or been to a chicken house, you really shouldn't say anything. If all you've ever done is watched YouTube videos, you don't have a clue what you're talking about. Because I've raised chickens on pasture that are the same kind of chickens that are raised in a chicken house, and I can guarantee you those chickens are not bred to be raised on pasture. They are bred to be in a chicken house with the perfect moisture, perfect water, perfect feed, perfect heat and cool. My chickens didn't live very well because I wanted them to go outside. They didn't want to go outside. And so it didn't work real well. But until you've done it or talked to somebody and know, you're going to look at those videos and say, oh, that's terrible. Those chickens have such a terrible life. And you don't even know. And so those are the things that I tell you that for. All right, keep going on radioactivity. So what is radioactive decay? I pretty much have already answered that, but let's talk about it again. It's the process by which an unstable isotope emits radiation to form a more stable isotope with a new composition. And that's what we were talking about. It's a new element. A new element is formed.
Okay, so if like radiation is like a nuclear change, then like why does beta radiation, like why is that electron?
Because I can't explain it all.
Okay.
There's neutrons that are happening. There's protons that are happening. One of the things that often happens, and we're not going to even do nuclear reactions. I'm not ever going to say to you, I want to know what phosphorus-32 breaks down to form when it decays. I'm never going to ask you that. That's a much higher course than what I'm teaching. But I do know that a lot of times when you have nuclear decay, not only do you get one particle, you get others. So in other words, you may be getting beta particles and gamma rays and positrons all. So I'm not saying exactly which one always emits which one. I am going to say iodine-131 emits beta. Now, does it emit other? It may. I don't know. Okay? What I want you guys, this is preschool. Literally, that's where we're teaching. What I'm trying to get you guys to understand, you are going to be in the medical field, most of you. You are either, every one of us, whether it's personally or a patient that you have or a friend or family member, every one of us, very, very likely, by the time we pass away, will have known someone who undergoes nuclear treatment. I mean, it's coming to that point. Somebody is going to be affected by it that you know. And if you don't know a little bit about it, the fear is too great and you can't think reasonably. And that's what I'm trying to overcome. That's what I really am trying to get you to realize. Okay? Just give you a little bit of knowledge. If you want to dig deeper, dig. But I'm just giving you the very minimum to get you over, hopefully, that fear. Before we talk about hyperthyroidism, let's come down. I want to show you, this is what I really want you to see here. So phosphorus-32 is radioactive. After 14 days, which is called its half-life, and I'll describe that in a minute, you only have 8 grams of phosphorus-32, which again is radioactive. But you also have 8 grams of sulfur-32, which is not radioactive. So what has happened? The radioactive decay has caused the unstable phosphorus-32 to break down to form what? Stable sulfur. Do you see that? That's what I want you to see. So we go from unstable to stable. After another half-life of 14 days, what do we find? It's cut in half again. But what's increased? So again, we have unstable, less unstable, more stable. After another 14 days, less unstable and more stable. Eventually, what's going to happen? Virtually all of it is gone. And then the question that somebody has is, well, what happens to the sulfur? Sulfur is in your body anyway. You're just going to flush it out of your system. Yes, maybe your urine will stink. I don't know. But it's going to go out. It's not going to, and even if it stays in, it's not going to hurt you because it's not reactive. So basically the radioactivity is going to be targeted. It's going to be where it needs to be, doing what it needs to be, and then moving on. It's not going to stay and do damage any longer in any more places than it has to. That's the goal. That's the goal. So what is a half-life? A half-life is symbolized T sub 1/2. If you see, and that's not a Y, that's 1/2. T sub 1/2. And it is the time it takes for 1/2 of the sample to decay. It's the time it takes for 1/2 of the sample to decay. Naturally occurring substances generally have very long half-lives, but radioisotopes that are used in medicine have short half-lives, so they do not linger. We don't want them staying in your body. We want them going out of your body. That's the goal. And so they have a very short half-life. Some examples of naturally occurring Isotopes, you have heard of some of these. Carbon-14, it is 5,730 years. Uranium-235, 7.04 times 10 to the 8th years. And somebody wants to ask, what? How do they know? My assumption is that it's extrapolated. It's one of those things that they have watched it over so many years and then estimated what it would be to finally be. And so they've extrapolated it out. Obviously, nobody's lived, to our knowledge, 5,730 years, or this is 700 million years. That's a long time. So, but they are very long half-lives. Radioisotopes used in medicine, iodine-131 has a half-life of 8 days. Fluorine-20 has a half-life of 11 seconds. Technetium-99m has a half-life of 6 hours. The shorter half-life isotopes are typically used in diagnostic testing because you just go have the scan that you're having done, you want it out of your body. If you are being treated, it's going to last a little longer, and that would be the iodine-131. So let's look at how iodine-131 is used. This is really neat, and I think it's a good explanation of the fact that it's targeted medicine. So hyperthyroidism. Go ahead.
About the TC99M.
What does the M stand for? I do not know. I do not know. It's just the name of that particular isotope, and I don't know. All right, the hyperthyroidism. What is it? What does hyper mean? Overactive thyroid. So if you have an overactive thyroid, your thyroid gland is working too much. In order to slow it down, what's one of the options? Cut part of it out? That's one of the options. Cut part of it out. Okay, do we typically want to do surgery? That's not usually the first thing you want to do to somebody is have surgery. It may be an option. It needs to be considered an option. But typically, if you don't have to cut on somebody, don't cut on them. So another option is to use iodine-131. And the way this works is pretty neat. Thyroxine, this is the molecule thyroxine. And thyroxine is used by the thyroid. Nothing else uses thyroxine but the thyroid. So thyroid, or thyroxine rather, already has iodine in it. It already has atoms rather of iodine. So what they do is instead of using stable iodine, they use iodine-131 in this thyroxine molecule that they make. You take the pill of thyroxine, and that thyroxine goes to your thyroid gland, and the beta particles that are emitted from the iodine kill the thyroid gland. So instead of going in and having to cut it out, the beta particles do it. It then reabsorbs, passes on, decays into something stable. I don't know what it decays into. It doesn't matter for our purposes, and goes on. Is it better than surgery for a patient who doesn't heal well? Yes. Is it 100% perfect? No. Is surgery 100% perfect? No. In both cases, could you kill too much of the thyroid gland? Yes. And I've had students who've had either themselves or family members that underwent this treatment, and sometimes they killed too much, and then they still had to take the hormone, and so it was still a problem. It's either or. There's going to be not a perfect answer. But this is something that what I'm trying to get you to realize is And this is something you would be, as a nurse, telling your patients, thyroxine is used by what? The thyroid gland. Is it going to kill the cells in my arm? Is it going to kill? No. What's it going to be used by? The thyroid gland. And that's what's really neat about radioactive isotopes is they're used in targeted medicine. They're targeting a certain area. So let's do some problems here. So run down to the bottom and do these math problems at the bottom of the page. Not hard. Run through those. Who didn't get the sign-in sheet? All right, so I don't care how you do this problem. You can do it on your fingers. You can do it in your head. I don't care. If you want to see a written explanation, you start with 1 gram. After 1 half-life, you have what? 0.50 grams. After another half-life, you have what? 0.25 grams. And to use proper significant figures, what would you do? How many do you have to begin with? So you put 0.250 grams. Don't make these hard. Don't make these hard. All right, the next one. What do you have to do first in the next one? What do you have to figure out first? How many half-lives there are. And so it's 24 hours. 1 half-life is 6 hours. So that is 4 half-lives. So once you know how many half-lives there are, you can simply do the same thing we did earlier, or you can set it up 1 half, 1 half, 1 half, 1 half, and do the math, and you see it's 10 milligrams. Yes or no? You will see some half-life problems on your homework, and there will be something on your exam about half-lives. All right, radiocarbon dating. Have you all heard of that before? Up there with eHarmony? What is that called? Farmersonly.com. That commercial on MeTV. I haven't seen that lately on MeTV. Farmersonly.com. Is that how it goes? All right. My daughters do that. I hadn't thought about that in a long time. They used to do that. All right. Carbon-14. They called it carbon-14 dating. Carbon-14 dating. Where have you heard of it before? Fossils, dating fossils. Good. All right. How does it work? All once living and living organisms contain carbon. I think we all agree with that statement, yes, based on what we learned last day. Who's the most abundant element in the human body? Oxygen. But they all contain carbon. Here's the key, though. They contain both carbon-12 and carbon-14. Carbon-14 is decaying over time, while carbon-12 remains constant. Now let's think about that statement for just a minute. Carbon-14 is what? Stable or unstable? Unstable. It's a radioactive isotope of carbon. We have carbon-14 in us, along with carbon-12. Okay? The carbon-12 is stable, though, so it is not decaying. But carbon-14 is decaying. By comparing the ratio of carbon-14 to carbon-12 in an artifact to a living organism, they get a relative age. Now, is it perfect? No. Is there controversy about it? Yes, there's controversy about it. It is done, and there are other radioactivity methods to do the same thing with. The key that I want you to get, though, is the fact that you contain radioactive isotopes. Now, one of the days that I was teaching this lecture, I had this thought all of a sudden, and I don't know that I'm right at all, but I just want to throw it out to you and let you hear the thought. You know how there are some people who are 90 years old, but they look like they're 65. I mean, they're just in really good shape, and you just wouldn't know they were very old at all. But then there's other people who are 65 that look like they're 90, and they have just aged dramatically. Now, you realize that environmental factors play a part in it. I'm not talking about environmental factors, but it hit me one day. Could it be that all humans don't have the same ratio of carbon-14 to carbon-12? Could it be that humans that get older faster, decay faster, actually have more carbon-14 in them and less carbon-12? And people who look young when they're old have more carbon-12 and not as much carbon-14? And I don't know the answer, and I don't know if anybody's ever asked that question before. And I'm not smart enough to research it, so maybe you all can take that on and find out. But that is one of those I wonder questions.
It could also be just how the random decay of carbon-14 went in your body.
And it could be, and that could be environmental, possibly. But they say that the decay, the half-life is consistent. With
throughout the half-life, it's random when the decay.
It does? What's your major anyway?
Oh, my major's computer.
Oh, but he knows this stuff. Tell me how you know this, though. Tell me how you know this. You've read it. And so that it's random. How is it random, though?
It's random to a degree.
Because they say half-life is independent.
It's based on the probability of decay happening. At that time, half of it will be gone.
But you do. I'm with you. So in other words, over 10 years, the decay, the first 2 years might be no decay, and then 8.
Yes.
I've gotcha. Okay. And environmental can make a difference in that? Don't know? Okay. Well, the other thing is we also have other radioactive isotopes. Potassium is another radioactive isotope.
So do you think you could use C12 as like a beauty treatment?
I have no idea. I doubt it. I doubt it. I doubt it. I'm not going to worry about it. Are you going to? I'm not going to worry about it. I'm half over, so I'm good. But I'm not going to worry about it. But again, it's one of those interesting things, and I don't know if anybody's ever researched it. I have no idea. So, but anyway. All right, so how do they detect radiation? How do they detect radiation? One of the ways is with a Geiger counter. And if you ever get a chance to play with a Geiger counter, it's pretty fun. It's a handheld device that detects radioactivity. And it clicks when radiation is detected. It's kind of like a metal detector. So you just have it and you're holding it, and if you get to this area that has some radioactivity, it's going to just make the clicking sound. And it will measure it too. But your chances of ever seeing a Geiger counter are probably kind of slim. But you might find one sometime and get to play with it. Where you guys are going to be tested for radiation, for many of you, a radiation badge. And that detects exposure. That detects exposure to radioactivity with a photographic film that fogs after exposure to radioactivity. It detects exposure to radioactivity with a photographic film that fogs after exposure to radioactivity. Do any of you have a radiation badge or had to wear a radiation badge?
I have a question.
Okay.
The first one, the counter.
Geiger counter?
The guy in the Chernobyl diaries is using when they're walking around.
Probably, yes. Is it handheld? I've never, is it a TV show?
It's a movie.
Okay, I've never seen it. Yes, I would imagine it probably is. Does somebody know? I would say it is. Now, if you're interested in Chernobyl, there is an interesting article. I have not read the entire article, but it's on Blackboard. One of my students found it, and it's I think, under the announcements. Look in all the announcements. I think it's in the announcements. It may actually be in the lecture material. I can't remember, but there is an interesting article. If you don't find it, send me an email. But I think it's there and open. And I've read part of it. It's very interesting, though. All right, let's talk about the radiation badge. Did anybody have a badge? Okay. All right, the badges, first of all, this is funny because there's going to come a point, and you guys still know this, but there's going to come a point, and when I get to this point, I'm going to quit teaching, that people will not know what photographic film is. And it's coming soon. Because very few of you, I bet, have ever used a film camera. Some of you have, but probably some of you haven't ever used a film camera. Well, film is black and white film. I can't tell you exactly how color film works, but black and white film has a coating of silver nitrate. And silver nitrate changes to black when it is exposed to light. And so film in an old camera, a 35 millimeter camera, when you had that film, you would put the film in and get it to click over on the cog, and then you would put the lid closed, and then you would crank it a couple things, take the shot, crank it again, or it's an automatic winding one. And what you never did is open the back. Because if you open the back, you ruined your whole roll of film. Now, all that explains film is going to detect light. And light is energy. You with me? So this badge that you wear is in a plastic case that can't get any light to it. But what is radiation? Emitting energy. And so if it gets exposed to radiation, it changes as if it were in light. But it's changing because of the radiation, because no light's getting to it. And so what they do is they check that badge every so often and see if it has been, see what your exposure to radiation has been. And I've asked this question, nobody can give me a good answer other than OSHA. But I've asked the question, it doesn't seem like a good system because you check it after you've been exposed. And you don't know that you've been exposed until you've checked it. Does that make sense? And so anyway, they couldn't tell me why they do that. I guess there's not a way to measure it. I think what they're basically doing is you shouldn't have any exposure if you're following protocol. And if you don't follow the rules, then you're going to be exposed And we're going to check every so often to make sure you're following the rules is probably what it boils down to. I don't know. When you guys get in your job, you can come back and tell me because I don't know the answer.
Isn't there film in like the disposable cameras?
There are film disposable cameras, yes. There are yes, I think they still sell those. Yeah, I think I've seen them. All right, so 2 ways to measure radioactivity just in a general way with no numbers. I guess that'd be the no number way. Then when we get into numbers, Becquerel and Curie are 2 of the units used. Do not highlight those. You're never going to have to memorize. 1 Becquerel is 1 disintegration per second. 1 Curie is 3.7 times 10 to the 10th disintegrations per second. What I want you to realize is if you were truly looking at the numbers of radioactive decay, then you are looking at how the nuclei decay over time. That's what they're looking at, is how it decays over time. Let's do the math problem, and then we'll talk more about the units, because I know you can do the math problem. Do the math problem. You should be able to do this without knowing anything other than dimensional analysis. Do you get 1.3 milliliters? Okay. All right, so 1.3 milliliters. Now, what does this mean? If you have to administer 4.5 millicuries to a patient, and the solution comes 3.5 millicuries per milliliter, then you will give them 1.3 milliliters. What would this be for? I don't know. I'm assuming hyperthyroidism. I do know, though, the hyperthyroidism that we talked about earlier was using a pill. I know that can be used. But perhaps it's a solution as well. Obviously, with this question, it is. As far as understanding when or why the question, that's what you'll get in a nursing class. That's not my job. My job is, can you do the math? And you should have been able to do the math week 1 or week 1.5. So that shouldn't be an issue. Now then, let's go back up, though, and talk about nuclear medicine for a minute. Just in a general sense, I knew people who were born in 1902 and 1913. I've had grandparents who were they were born during those years. For me, early 1900s honestly doesn't seem very long ago. Now, I mean, I realize it was over 100 years ago, but it just doesn't seem that long ago to me. So to think that Becquerel, Mr. Becquerel, discovered radioactivity in 1896, that tells me it's pretty new. And I don't know if you've realized that or not, but the knowledge that we have of radioactive elements is new knowledge overall, very new knowledge. Marie Curie investigated more radioactive elements and discovered radioactive elements in the early 1900s. So within the lifetime of people I knew, she was doing her work, and she wasn't that old in the early 1900s when she was doing this. She was born in 1800s, but she was doing this work in the early 1900s. Now, the elements from 84 on, 84 all the way, and there are more elements discovered now past 104. You can find that online. But from 84 on, there are no known stable isotopes. That means every element past 84, they're all radioactive. There's none that are stable isotopes. Polonium is an element that Marie Curie discovered. And the story, if you all need to have a story or a paper for a literature or for a writing class, look her up, because this is, do you know about Marie Curie? You may know about her. Some of you do? No? Some do? No? Really neat story. So Marie was born in Poland. But in Poland, they would not let women be chemists or physicists. So she could not be what she wanted to be. She couldn't be a scientist. So she and Pierre, her husband, moved. I don't remember where they moved. They moved to another country. Then, while they were studying and doing their research, they discovered polonium. But she named it polonium. Why? Because she loved Poland. I think that's pretty nice, because they kicked her out, but she still loved her country so much that she named it after her country of Poland. So, okay, that didn't throw you. Let's move on. All right. So now, polonium actually is radioactive. Fast forward. Just so you know, Marie Curie died because of radiation exposure. I don't know about Pierre, but probably he did too. I don't know that, but I know Marie did. Now, go backwards. She's still alive, and they are in their lab, and they have polonium, which is radioactive, but they really don't know what it's going to do to you. I mean, they have it out. It's just, they're, carrying it around. It's just hanging out all over the place. Look, it's glowing. Look, Pierre, how cool is this? They have 2 little girls, normal little girls. Now, for me, that was like, wow, because I couldn't have kids naturally. So anybody that can have kids naturally is like amazing to me. But then the fact that you were whacked out with radiation and you still had kids naturally, I was like, wow, that's pretty special. So then, keep going on special. Marie and Pierre win Nobel Prizes. Their daughter wins a Nobel Prize. Her husband wins a Nobel Prize. The other daughter moves to the United States, wins a Nobel Prize. And then you're like, give me some polonium, right? Because it's like, wow. But what's neat to me, and I know there are a lot of really bright people that are still alive, but that story of that family has always intrigued me. And what's cool, if you look them up, one of the daughters moved to the United States, New York, I think, and then they had children, and they're still here in the United States. I mean, wouldn't that just be wild to run into Marie Curie's grandson? Or, and you have to think they're not that old. Because really realizing she was in 1900s, those generations, they could be my age. The grandkids could. And so, obviously she probably had her daughters pretty young. But it's just kind of a neat, the whole fact that that she died of radiation, and probably Pierre did too. And the fact that they had these children that were normal, or maybe extremely bright beyond normal, but it just is a neat. I don't know. Look them up if you want a story to write. I thought that was a neat story. Becquerel may be as interesting. I just haven't studied Becquerel. All right, so absorption. How do we measure how much radiation we've been exposed to? And let me say this before I go any further. If you're really interested in this, something that I do not know that I would like to know but have not taken the time to look up is the relationship between Becquerel's or Curie's and absorption. So in other words, let's say that you're given this many millicuries. How does that relate to rad and rem? And I don't know the answer to that. I'm sure there's a way to figure it out, but I don't know the answer to it. But rad and rem are methods of measuring the energy absorbed by a substance that has had the exposure. They're both methods of measuring absorption, but they stand for 2 different things, and I want to tell you what they stand for and then tell you which one's used mainly today. They're, in a sense, generic terms. They're radiation absorbed dose. That's rad, radiation absorbed dose. And rem is radiation equivalent for man. Radiation equivalent for man. The rad does not take into account the type of radiation or the absorbing substance. It does not take into account the type of radiation or the absorbing substance. And I think you all would agree, would bone and muscle and fat absorb differently? Yes, and so that's what I'm saying. It does not take that into account. The rim, however, does take into account the type of radiation and the absorbing substance. So it takes both into account. The rim is what is mainly used now, and it is the preferred method of measuring. So we mentioned earlier that we are all exposed to nuclear radiation. So let's look at some ways that we're exposed. Radon gas. I don't know if there's a sign anywhere around now, but there was a billboard here in Warren County that talked about, have you had your house checked for radon? When I was in college, there was a big push for a while here in Warren County to have your home checked for radon gas, because they said that we were, because of the cave system underneath all of our houses, we are a pocket for radon gas, because the radon gas would just exist in the cave system, and then it just comes up through the ground, and it gets into your crawl space, and then it just rises up into your house, and you're exposed to the radon gas. Radon gas, the danger in radon gas is it causes lung cancer. And so I don't know if the statistics have, I don't know if they've actually checked this or not, but I know that they were talking about how, and again, this was 25 years ago, they were talking about how obviously, you know, lung cancer is caused by smoking, or smoking can cause lung cancer, and then radon gas and smokers we're going to have even higher risk of lung cancer. So in other words, if you were a smoker in Warren County, you were going to have a higher risk of lung cancer than if you were living elsewhere without the radon gas. And so that was why it was a big push. Have any of you ever heard of or had your house tested for radon gas? Have you heard of it, though? Where have you heard of it? I mean, what? So he talks about it. Does he talk about, is he here locally? Does he talk much about, I mean, is it still... And so he's learned about it from there and the dangers of it, yeah. Most of the houses nowadays that are built, and probably even older houses were done the same way for different purposes. They'll put plastic, a thick layer of plastic under your crawl space, and then that stops it from coming up into your crawl space. And that was one of the, and then making sure you have ventilation under your house. That's why you have the vents. But all of those were also remedies for other things as well. And so it wasn't just for the radon gas, but that was one of the big pushes. All of us are exposed to it, though, and that's where a large amount of our annual exposure comes from, is from radon. Now, I don't know in Warren County if it's higher than 200 that we're exposed to. I don't know. Don't have a clue. Medical sources are going to be some, and then just the radioactive atoms in the body, where that's a large amount of just the radioactive anything we've been exposed to in our body. And that's where we were talking about. You can't get away from that. You live with yourself. You can't get away from that. And so here, when they're talking, this came from your textbook, the free textbook online. They wrote it as 14C. What would I write? Carbon 14 and then potassium 40. And so those are two isotopes that are radioactive that are in your body. And you can't avoid that. You can't avoid the natural. I don't know what the consumer products are that they're talking about, but I do know that there was a glass, and I cannot think what type of glass that was. Do you know? That emitted radiation. There was a type of glassware. you know how Fiesta ware, I'm not saying it was Fiesta ware, but I'm saying it was something like that that emits radioactive energy. And I don't remember which one it was. So we're exposed. All of us are. Whether we want to be or not, we're exposed. So what are the effects of exposure? So we're exposed, so what's going to happen to us? Well, did you notice that that was 358 millirem? Did you notice that number? Well, you can have up to an entire rem over a full year, and you're not going to have any effects. You're not going to know it at all. You won't know you've been exposed. No problems at all. Approximately 20 rem a year, you may have an increased risk of cancers, of some cancers. In medicine, if you have up to a 25 rem dose, then you may have some sickness, just like you would if you had 25 to 100 rem dose. And that can be used. A 25 to 100 rem dose can be used in medicine. And yes, your white blood cell count may be low. You may have to be kind of in seclusion. And you know people who've had this happen before, whether just from chemotherapy or from nuclear radiation treatment. And you know what I'm talking about, or they may have nausea, they may have illness, just feel bad. Those are all some of the symptoms. And then if you have approximately 600, you'll be dead. So there's a huge range of what hurts you at all versus what kills you versus you're not going to have any effect. So how's it used in medicine? This picture came from the 109 McGraw-Hill book. And this is what we were talking about. If it's used in diagnostic testing, it's going to have a very short half-life, and you're usually going to ingest it or inject it. It's probably going to be used in a scan of some form or fashion. So looking at these on this side, you see technetium-99m used in 3 different situations. One is a bone scan, one is gallbladder function, and one is gastrointestinal bleeding. All of those are what kind? Diagnostic or treatment? Diagnostic. All of those are for diagnostic testing. What was technetium-99m's half-life? Do you remember? 6 hours. Does that make sense? You're visualizing something, you want it in and out, be done with it. That would be short. That's good. Xenon-133, I don't know the half-life. It's used for lung function. That's also diagnostic. That's diagnostic. For treatment procedures, it is usually either external or it can be internal. It can be either one. It's external mostly with gamma rays, and that's where we were talking about the cobalt-60 being focused on a tumor. That's the scenario I already gave you about cobalt-60. Yes, you definitely are going to have some radiation illness from that. That's definitely some high-powered radiation that you're getting. Internally would be a lower dose of radiation. And internally, that would be what we were talking about as far as the iodine-131 with the thyroxine. It can also be used in certain cancers. Literally, they take a wire that has been impregnated, or a seed, like think of a BB or something, that has been impregnated with this isotope that's radioactive, and they implant it near the tumor. So instead of going in and cutting, yes, they have to go in, but it's a very small incision, and they're putting something in there that's radioactive that, while it's there, is emitting the radiation that's killing the cells around it. Iodine-125 is used like that in some prostate cancers. Now, prostate cancer, your options, if you and girls, you don't ever get prostate cancer. That's a good thing. You don't have to worry about prostate cancer, okay? But in prostate cancer, your options are usually cut the prostate gland out, and most men, especially young men, do not want that to happen, or do something to try to kill the cancer. And so then the thought is if they are going to go in, you want to only kill what's necessary to kill. And so that's why they will use that radioactive wire near, and it's used in bladder cancer also. I know it's because I knew someone who had this down in bladder cancer. They just put it near that organ, and then it targets that area. So they try to use nuclear medicine very targeted, and I really tried to stress that because I want you to realize it's not just a massive, here, let's send them in the gamma ray chamber and zap them like the strawberries. You know, we're not going to do that to people, okay? All right, some isotopes that are used. Which ones have I talked a lot about that are on this list? There's one for sure. Iodine-131, technetium-99M, and you have seen phosphorus-32. I'm not going to ask you to memorize all those, but you should recognize the ones we've spent a lot of time talking about. Oh, one thing I do want to point out on that page that I didn't mention. We were talking about phosphorus-32. It is sometimes used to treat some leukemia and lymphomas. We've already talked about the iodine-131. So this is treatment. This is treatment. Iridium-192 can be also used for treatment. But this is what I wanted to mention here. In Bowling Green at the medical center, the Bowling Green Medical Center does not use radioactive isotopes to treat breast cancer. They use X-rays. Now, I'm not saying that there aren't places that do, because there are places that do. A friend of mine underwent breast cancer treatment, and she did have a radioactive isotope. But the medical center uses X-rays to treat breast cancer because they also are high energy. Now, I'm sure if different forms of breast cancer need higher power treatments, then they go to other places that do the nuclear radiation, but the medical center does not. And so I don't want you to think all breast cancer is iridium-192. That's not true. That is not true. We mentioned PET scans, so let's look at PET scans and some other imaging techniques that are not nuclear radiation. A PET scan is positron emission tomography. And I'm not going to expect you to know all the details, so I'm just going to simply say it uses positrons. Uses positrons. It uses other things as well, but I'm going to keep it simple. What do you know about PET scans? Tell me anything you know about PET scans. I mean, it can be what's written here, but tell me more about what you know. Where have you heard of PET scans? Somebody in here knows something about PET. Thank you. She had a stroke. They did a PET scan on her brain. Good. What else? It does read the isotope. It reads the activity of what's working with that isotope in the body. Nobody else had anybody in the family who had a PET scan?
I didn't know she had a stroke before she had a PET scan.
So she had why did she have the PET scan then?
Because
Something was wrong, and then they detected that it had been a stroke. They had symptoms, and then they did the proving that she had the stroke. Proving what part of the brain? Put your phone up. Proving what part of the, all the way, please. Proving what part of the brain had the stroke. Nobody else has had anybody that had a PET scan for like cancer or to check and see? And she didn't, so they thought.
They performed surgery on her and that paralyzed me.
Oh my, wow. And so then they found out she didn't have any, so it's lots of times it's used to detect hot spots. That's what they will do. They will use a PET scan to detect hot spots. If a person has had cancer, it may have been detected with a PET scan, and then after they've had treatment, they will do a PET scan again to detect whether the cancer is gone. And you're correct, the isotope, I don't know if it's the isotope you take that emits positrons or the instrument is emitting, I don't know how it all works, but I know that when the scan is being, let's say that you had cancer or you do have cancer, you don't know you have cancer, but they give you this isotope, and if it's a fast-growing cell, which is where cancer would show up, that part is going to glow on the machine. Now, that is what I knew about PET scans when I started teaching this class 5 years ago. I knew that it was used for detecting cancer in organs of the body. That's what I knew. I knew it was for tumors. I knew that's what I knew. Colon cancer, that would be definitely what I was thinking. I still don't know how it is used in coronary artery disease. I have no idea on that one. But this is the one, the detecting stroke and Alzheimer's, that's the one that was brand new to me. And so what you were talking about, for me, when I found out about that, I was really excited. Because when I started teaching this class 5 years ago, my dad was starting to have signs of dementia or Alzheimer's. And he was losing memory. He was having problems. And so immediately when I read this and I'm teaching this class, I'm thinking, Daddy needs to have a PET scan. And he'd had PET scans before because of other things. I'm like, we need to have Daddy have a PET scan. We need to see what's going on. We need to see if he has Alzheimer's. And they said, no, we don't need to see if Daddy has Alzheimer's. He was 83. Why? I just told you the answer. He was 83. And is there any cure for Alzheimer's? No. So did it matter if Daddy had Alzheimer's or not? No. Was there any different treatment for him if he had Alzheimer's compared to dementia? No. They're going to treat it the same. There's no reason to do a PET scan to see if he's got Alzheimer's. Now, it doesn't matter. He doesn't think straight. He's lost his memory, a lot of it, but he's sweet and gentle, and that's okay. We still love him. But it wouldn't have mattered. But for me, that's what I was thinking. Oh, let's find out. But if there's no reason to find out for someone who's 83, then there's no reason to do it. Now, with that said, your aunt was having symptoms. How old is your aunt? She's young. Your aunt was having symptoms that were unlike a 53-year-old. Then they go in and say, what has happened in the brain? And they find out it's a stroke. Because what does the stroke affect? The brain. What does Alzheimer's affect? The brain. Now, how it works is neat. It's really, really neat how PET scans work to detect those problems in the brain. What does your brain prefer to use for food? Does anybody know what your glucose? Your brain likes glucose. I love it when my videographer answers questions. I love that. No, I love it because you're engaged. That's awesome. Thank you. No, Ryan does the same thing. It's awesome. I love it. And so glucose, your brain uses glucose. It prefers glucose. So what they do is they put a tag, they incorporate isotopes that are radioactive on glucose. And then, I don't know if you drink it or they inject it into you. I don't have a clue. But what immediately is going to start using that glucose? Your brain. And so let's say that they do this to me and they take me in and they scan my brain and they have all this activity all over the place except right there. Right there is black. That means there's no activity there. That means that part of my brain is dead. That then explains the symptoms that I'm having. Now, and I don't know, I'm feel confident there is a certain place in your brain that's the Alzheimer's place. I don't personally know where it is in the brain, but that's how they detect that it's Alzheimer's, because they know the part of the brain that's affected in Alzheimer's patients. Used to, you had to die, then they said you had Alzheimer's. Now they can detect it earlier. So if I or your aunt who's younger, if we have those symptoms of Alzheimer's or stroke, yes, they will test. Yes, they will find out what's going on. Because if I was acting like my dad acted, then they would say, is it a tumor? Is it a stroke? Is it Alzheimer's? And if it were Alzheimer's, what are they going to do with a younger person compared to an 83-year-old? they're going to be actively treating it. Would I be the guinea pig? Would they be giving me things that are experimental, or would I try to have that? Absolutely. They would be doing everything they could to figure out how to help a younger person. But an 83-year-old, they're not going to. They're not going to do that. And so that's the whole, that was to me, though, such a real, I'm just amazed at how medicine over just in my short life, really, and you see that, just radioactive work has just been in 100 years, basically. And how we have just learned so much, even in the last 20 or 30 years, to be able to use these techniques to learn from. And that one is relatively new. I don't know when they discovered that, but it's relatively new. Now, nuclear fission, on the other hand, has been around for a while. You know a little bit about this. It's the splitting apart of a heavy nucleus into lighter nuclei, neutrons, and energy. The splitting apart of a heavy nucleus into lighter nuclei, neutrons, and energy. Nuclear power and nuclear bombs. That's where you have heard of fission, if you didn't know you'd heard of it. It's the splitting apart of a heavy nucleus into lighter nuclei, neutrons, and energy. So how does that work? The uranium isotope, and I want to tell you right now, I have seen different isotopes listed as the isotope. I'm not going to put a particular one here because I've heard there's different ones. I thought it was 239, then somebody else said it was 238, then 235. I'm not going to list it. It's a uranium isotope that's a radioactive isotope. By the way, uranium is naturally occurring in Colorado. And the uranium, it's you know how iron, have you ever heard of fool's gold? Okay. Fool's gold is iron ore. Any of your metals that are in rocks are called ore. So fool's gold is iron in rock, and that's called iron ore. Uranium ore is uranium in rocks. And in Colorado, there is quite a bit of uranium just in the rocks. So the Geiger counter causes the rocks to click. And that it's in the rocks, in there. I have some uranium ore at home. But anyway, it's aside. But I forgot to tell you about that earlier when I was talking about the Geiger counter. I'd forgotten about it. But anyway, so the uranium isotope that's used in nuclear reactions, the way that works, the uranium isotope is bombarded with neutrons that cause the uranium to split. That continues in a chain reaction. So you just have that continual, the neutrons bombard, breaks another one apart, produces neutrons, breaks another one apart, and then that's just a continual chain reaction. Now, in a power plant, this reaction is producing heat. So what is going on, based on your knowledge that I already told you about, or your prior knowledge of power plants anyway, tell me how that works. It boils the water, which the water then turns the steam turns the turbine turns the generator, produces electricity. So good, you've got that. So that's how the nuclear power plant works, and the nuclear power plant is controlled. There's only so much of the uranium available in the reactor. It's kept cool. It's not allowed to overheat until that meltdown that occurs. But overall, it's a controlled reaction. So power plant is controlled. the bomb is uncontrolled, because enough uranium is present to reach what they call critical mass. Have you ever heard of that term before? Critical mass is the amount, and I don't know what the amount is. I don't know what critical mass is, but it is the amount that's necessary that causes this to get so hot that it explodes. And that's what's happening in a bomb. That's what happens in the bomb. Albert Einstein worked in Oak Ridge, Tennessee on the nuclear bomb, and that's one of the things he regrets. He regretted working on that because of the damage it caused. But he did work on that process of getting that energy to be so great, to the whole process of all that work. He was one of the people that worked on that. Nuclear fusion is the opposite of nuclear fission. So fission is the splitting apart. Fusion is the joining together. So nuclear fusion is joining together two light nuclei into a larger nucleus. So in other words, they literally join together to form a larger nucleus. The sun produces its energy by fusion. Do you remember me mentioning Tuesday to go see the planetarium show about the stars? This is the reaction that they talk about in there. Deuterium, because this is how stars and sun, the sun is a star. You know that? Okay. Deuterium plus tritium yields helium plus a neutron plus energy. Deuterium plus tritium yields helium plus neutron plus energy. Now let's figure this out. This is very good review for last class period. Tell me about deuterium. Tell me what you know about deuterium. It's hydrogen, good. Keep going. It has a mass of 2. How many protons? 1, because it's hydrogen. Tritium has a mass of 3, and it has how many protons? 1, because it's hydrogen. So tell me about helium. What do you know about helium? It has 2 protons, and it has a mass of 4. Now think about that for a minute. You have taken hydrogen, deuterium, with its 1 proton. You've taken tritium with its 1 proton. This one has a mass of 2 AMU. This has a mass of 3 AMU. And you have been able to join them into 1 nucleus. 2 independent nuclei to 1 nucleus. And it had a mass total of 5, but what got kicked out? A neutron. That's where that neutron came from. And in the process of fusing this together, you get energy created. The sun, that's how the sun is created, and that's how the energy is from the sun. If we could figure this out, what would we have? Energy. That's no pollution energy. We can do it. We can do it. We have figured out how to do it a little bit, but not continually, efficiently. the National Ignition Facility actually has worked on this, because think about it, if you could drive the car down the road and produce its own energy just with hydrogen, would that not be amazing? And what would you'd get to, have balloons filled up all the time. I mean, wouldn't that be, you could float. It could be a car that you produce, drive off of hydrogen, and then you just float over the traffic. Would that not be awesome? Because you're producing that helium. So it is really neat if we could do it efficiently. The problem with doing it, though, think about one of the problems with doing it. And the thing about, I don't know if you guys know about these, so let me see if you can picture this, if you know what I'm talking about. Do any of you know what speaker magnets are? Do any of you know what speakers are? Yes. Okay. All right. In your car, there are round speakers. One of my former lives, I worked on my old car, okay? And the speakers, if you go find some old round speakers, they have, and I'm holding like this because it's a round dome on the speaker, and then here on the ends, it's a cone shape. It's like an ice cream cone, but here's the flat, and it's a circle. The ones I'm thinking of are circles about that big around, and the magnet's about that thick. All speakers have a magnet of some form or fashion, okay? So you have these two speakers, and if you try to take, and I used to do this in high school class with the biggest football player boy in the class, and I would have him come up and I'd say, okay, I want you to take these two speakers and I want you to put them together. And he's chuckling because he knows exactly what happens. As soon as you try to stick those together, they'll slip like that. You cannot get them to stick together. No matter how strong you are, those speakers, the magnets are stronger than you are. That's what I'm talking about here. To get two things that should not go together to be put together takes a lot of energy. Where would there be a source of energy that would allow that? But also the sun. The sun. Think about that. Where's the energy that it's the sun. So concentrating that, it's hard to do. It's hard to consistently do. So, but it would be awesome if we could all do that. All right, so all of that is nuclear. And unfortunately, we don't realize it, but some of the imaging that is with radioactive names or naming is not nuclear. These are the ones. This is not nuclear. So these are medical imaging techniques without nuclear radioactivity. These are radioactive, but not nuclear radiation. So X-rays, what are X-rays? X-rays are high energy electromagnetic radiation. High energy electromagnetic radiation. It is not nuclear. Tuesday we are going to see the spectrum, the electromagnetic spectrum that X-rays and gamma rays and UV rays and radio waves are all on the same spectrum. X-rays are on the same spectrum as gamma and ultraviolet. Ultraviolet is less energetic than X-rays. X-rays are less energetic than gamma. Radio waves are a whole lot less energetic than all of those. But they're all on that same spectrum. They're all on that spectrum. CT scans, CT stands for computed tomography. That's where the CT comes from, computed tomography. If you think of tomography as topography, you know what a topo map is? That's the computed tomography. It's a computer-generated image that's like a topo map of your body. That's a kind of a broad, crazy definition of a CT scan. But it's with X-ray slices. It's made with X-ray slices. It takes slices, it takes X-ray slices and creates a high-resolution image. If you ever get a chance to talk to a X-ray tech, they will explain the CT scan to you, and it really is cool. My husband had one a few years ago, and the X-ray tech let me come in and video it on my phone. He had one of his head, and I was in there videoing it, and then I brought it to class that night and showed the students. And then I remember, but I don't remember now. The guy told me that it was like how many millimeters thick each X-ray was. So in other words, it's, you know, the 3D printers? That's literally what it looked like as he was doing the CT scan, because it was like it was building his head with X-rays on the machine, on the screen as I watched it. That was what was going on. And so it was pretty neat how that works. And MRI, that stands for magnetic resonance imaging. That's what that stands for. And it uses low energy radio waves. If you have ever had an MRI, what do they put on your head? Headphones. And you get to listen to music because the outside noise is a really, really loud noise. And so it uses low energy radio waves. So it's very loud, but it is not nuclear. It's radio waves.
I was able to see one, but they said you couldn't have anything in there because
The magnet is really, really strong, and it'll, yeah. Yeah, right. Yeah. Yeah, usually it's cold, yes. All right, guys, Monday, be ready with the notes. Some of